right, welcome back to Cognitive Psychology. This is week 14, class number 1, and we're going to continue our look at chapter 12, problem solving and creativity. This time taking a look at problems from a new approach, specifically an information processing approach. And let's get right to it on our look at chapter 12 and the information processing approach to problem solving. So before we dive in, we're going to do a brief recap on two of the things that we need to be clear about before we start the information processing approach. The first one is just a reminder of what a problem actually is, because we are going to use the concepts of a initial state and a goal state in the information processing approach. Two is just a reminder about insight problems and the special properties that they have, because the information processing approach will be applied to insight problems to help us understand why something that has such a simple solution is oftentimes very difficult to figure out. So those will just recap in order to set up information processing approach. So we'll take a look at that approach, and then we'll take a look at specific ways of solving problems according to the information processing approach, which basically boils down to operator selection. So we'll talk about backup avoidance, difference reduction method, means ends analysis, and then circle back to insight problems to understand what makes them so difficult to solve. So first, let's start off with the recap. So what is a problem? As we discussed last time, a problem requires two things. Two criteria need to be met for something to be considered a problem. First criteria is that there's got to be an obstacle between your present state and your goal state, an obstacle between where you are and where you want to be. So in Kohler's chimpanzee experiments, he would set up obstacles between the chimpanzee and a banana. So the chimpanzee would be in the present state of being too far away from a banana to eat it, and the chimpanzee wanted to get into the goal state of being close enough to the banana to eat it. And the obstacle in between was not immediately obvious how to remove that obstacle. And that's criteria number 2. The obstacle cannot be immediately obvious in terms of how to get around that obstacle. That's what makes a problem. There has to be some sort of navigation or some sort of cognitive effort to figure out how do you get around that particular obstacle. So those two things are always required for a problem. A difference between your present state and your goal state, and no obvious way to get from your present state to your goal state. And we saw that with a bunch of examples last time. We'll just remind you of one of those. These are the wordies. And when you're trying to solve this wordie, you are in a present state of not knowing the common phrase or word, and you're trying to get to the goal state of figuring out the common phrase or word. So if this was just a reading challenge, if I simply told you, read those 3 words, that would not be a problem, because your present state would be not having read those words. Your goal state would be having read those words. So there'd be a difference between your present state and your goal state. But it is immediately obvious how to reduce that difference. You just say the 3 words, Daffy, Donald, and Mallard. Super simple, no obvious, it's an obvious solution. However, to guess the phrase is not an obvious solution. So that's what makes it a problem. So Daffy, Donald, and Mallard, you have to go through some cognitive work to figure out what that phrase is. It's not immediately obvious. So it is solved when you realize that Daffy is the name of a famous duck, Donald is the name of a famous duck, Mallard is another word for duck. And so we have 3 ducks. They're all lined up in a row, not in a column, but in a row. Hence, we have 3 ducks in a row, and the phrase is ducks in a row, as in, get your ducks in a row, as in, take care of business and move forward. All right, so taking care of that business, one quick final recap about insight problems. So insight problems are a special type of problem where people are unaware that they are close to a solution. So these are special kinds of problems because oftentimes we are aware when we're getting close to a solution. We are aware when we're solving the problem. So think about the problem of adding a 4-digit number to another 4-digit number, right? You know that you're getting closer to the solution. You know that you're going to add up the ones, and then you're going to carry, and then you're going to add up the tens, and then you're going to add up the hundreds. You know that there's a step-by-step procedure where you are getting closer to a solution. Another example, if you took my statistics course, you know that there is a 5-step procedure for doing a hypothesis test. So a hypothesis test is a problem, and there's a 5-step solution to that procedure. So you know you're getting closer to the end. You know when you're at step 4, you're closer to finishing this problem or finishing or achieving the solution than you are at step 2. So those are not insight problems. Those are a different type of problem. Insight problems are the ones where you don't know that you're getting close to a solution. You could be working on this for hours and you still have no idea if you're any closer to the solution than when you started. And this is because these solutions often only require one step. So we took a look at the haystack problem. Last time, the haystack was important because the cloth ripped. Why did the cloth ripping make the haystack important? And the one step that you need to solve this insight problem is to realize that the haystack became important because the cloth that ripped was a parachute. And as soon as you make that leap, as soon as you get that information, as soon as you come to that realization, it's very, very simple to solve the problem. And then we also took a look at the funeral problem. So I'll read it out one more time, just so you can recall. It goes, this is a story about a woman. While at the funeral of her own mother, she met a guy whom she did not know. She thought the guy was amazing, so much the dream guy that she was searching for that she fell in love with him immediately. However, she never asked for his name or number and afterward could not find anyone who knew who he was. A few days later, the girl killed her own sister. Question, why did she kill her sister? And again, this is not something that you can kind of step through and reason out and know that you're getting closer to a solution. You just have to realize that it's a one-step solution. She reasoned that if the guy appeared at her mother's funeral, then he might appear at another family funeral. And again, it's difficult to get to that answer, but why? Once you hear it, it's a simple solution. So why is it difficult to arrive there? That's what we're going to take a look at today. So these solutions only require one step for these special insight problems. So why would these problems be difficult? Well, we're going to see that when we consider problem spaces, and we're going to consider that right now. So this is where we're going to get now into the information processing approach, where we're going to take a look at how we represent a problem. How can we conceptualize that in terms of a problem space? So much like you can conceptualize your physical world in terms of length, width, and height, so that's physical space, you can conceptualize the problem world as a problem space. And we're going to take a look at that when we take a look at the information processing approach. And then we're going to take a look at how you navigate that problem space. How do you move through that problem space to get from where you are to where you want to be, to get from the start of the problem to a solution. And we're going to take a look at some strategies that psychologists have identified, such as backup avoidance, difference reduction method, and means end analysis. And then in the end, we're going to apply this idea to insight problems so that we can see exactly why a one-step solution would be so difficult to come up with. All right, so the information processing approach, we're going to illustrate this by taking a look at a very kind of classic problem known as the Tower of Hanoi. So this was invented by Edward Lucas in 1883. And what it is it's a problem where you have 3 locations and you have discs stacked on top of each other. And the number of discs can vary. We're going to start with the 3-disc version. And the goal is to move the entire stack to another rod. Typically, this is with wooden cutouts and rods that you put the discs on. We don't have a rod here, but move the entire stack from one location to another location, observing the following rules. So only one disk may be moved at a time. So you can only pick up one disk at a time. You can't move two disks at a time. Only the upper disk at each location can be moved. So in this instance, you would not be able to grab the red disk or grab the blue disk. You could only grab the green disk. And then the most important one is that no disk may be placed on top of a smaller disk. So you could not place the red disk on top of the green disk. You could never place the blue disk on top of the red disk or the blue disk on top of the green disk. So as long as the disk is smaller than the one that's underneath, you're fine, but you can't put a bigger disk on top of a smaller disk. So let's use this to illustrate the information processing approach. So the information processing approach has a few concepts that they use to represent what a problem actually is. It's a new way of representing a problem. So the first concept we need is the idea of a state. And a state is a representation of the problem in some degree of solution. So it's a representation of basically where you are currently in your problem. And we have a couple of special states. So we have your initial state, and that is your start state. So in the Tower of Hanoi problem, that's where you start. That's when somebody hands you the problem and says, hey, solve this. That's your start state. So in our example right here, having those three disks in position number 1, that's your start state. That is where you begin this problem. Your goal state is where you have the solution to the problem. So the start state is all three disks in position number 1. The goal state is all three disks in position number 3. So that's where we eventually want to get to. So we have the start state. That's where we begin. We have the goal state. That's where we end. And this is a problem because there's an obstacle between the start state and the goal state, the initial state and the goal state, and it's not obvious how we get there. And how we get there is by moving through the problem space and moving through intermediate states. And intermediate states are all the situations that you get to on your way to the goal. So these are basically the midway parts of the problems, the middle solutions, right? The middle parts of the solution. So for example, in the Tower of Hanoi, this is one of your intermediate states. At some point, you're going to have this configuration of disk, or you could have this configuration of disks in your solution. So we have all these ideas of states. And these states, the start state, the goal state, and the intermediate states, those are all used to create a problem space. And the problem space represents two things. It represents the various states of a problem. So the beginning state, the goal state, the intermediate states. And then very importantly, it represents the relations between those states. It represents which states are connected and how they're connected. And those connections, those are called operators. And an operator is a way that you can move between these states in your problem space. They're basically the rules of the game, the rules of the problem, the moves that you can make. So in this case, the operator would explain or would be the way of characterizing or representing the fact that you can only move one disk at a time, and the fact that you can only move the top disk in each location, and you cannot place a larger disk on top of a smaller disk. So let's start building up the problem space for the Tower of Hanoi. So we have our initial state. That's where we will start. And let's take a look at our first move, the first move we can make. Now, because of the rules of this game, because of the rules of this problem, we can only move the green disk, right? We cannot grab the red disk. We cannot grab the blue disk. You can only grab the top disk. So there's only two possible things we can do. We can take that green disk and we can put it into position 2. So if we apply that operator, so that arrow is an operator. If we apply that operator, we will end up in that intermediate state where we have the green disk in position 2. If we apply the other possible operator, we will end up in another intermediate state where we have the green disk in position 3. All right, so those are the only two possible first moves. We've started to build this problem space. let's keep building it. So those are the possible moves for your first move. Now let's begin with the second operator. So on the right, we'll begin with that intermediate state. And that intermediate state from there has two possible moves. So you can either take that green disk and go from position 3 to position 2, or you can take the red disk and move it from position 1 to position 2. Those are the only two things that you can do from that intermediate state. Now, technically, you could back up and move back to the initial state by taking the green disk and moving it on top of the blue and red disks. So you could back up and just go back to the beginning. You could say, whoops, I made a mistake, and I'll put it back where I was. So that's also represented in this problem space, because you can take the operators back. In this case, you can take the operators back to the previous state. However, we're going to keep building it up as if we're going forward. And on that intermediate state where the green disk is in position 3, those are the only two things that you can do. Now, if we take a look at the other intermediate state where the green disk ended up in position 2, those are the only two things that you can do. So then we continue to build the problem space, right? And we're not going to be able to do the whole thing, and I'll show you why in just a little bit. But from each intermediate state, you can define the moves that are allowed from that intermediate state. So we can define the operators and map out the intermediate states that are allowed from each move. And you'll notice that in this next level of moves, we actually have an intermediate state that ends up being exactly the same as the initial state, as the start state. So if you ever came to that state, if you navigated this problem space and ended up there, you would basically say to yourself, oh no, I'm back at the beginning. Shoot, let me try again. And you can see that from each of these particular intermediate states, you can continue to build up and build up and build up these connections, these operators to different intermediate states. And if you continue to build this, and we're ignoring about 2/3 of this just for illustration purposes, but if you continue to build this and to build this and to build this, eventually you're going to get to your goal state. So eventually, after traversing through all these intermediate states and all of these, using all of these operators, you're going to get to a position where you're at your goal state, where you have put all 3 disks onto another position. So now we have our goal state. Now we have our final state we want to get to. We have our initial state, which was the state that we started in. So we have our initial state, we have our goal state, and according to the information processing approach, solving a problem can be thought of as applying operators and navigating through your problem space. So the problem space gives us a structure where we can understand what cognitions are going through, and it can give us insight in terms of where we might find difficulty. So in this case, we could see that a successful solution to the Tower of Hanoi problem would involve this operator right there, leading you to that intermediate state, where you would apply that operator, which would take you to that intermediate state, and then you would apply that operator, that arrow, that gives you to that intermediate state, followed by that operator, taking you to that intermediate state, and so on, applying operators, moving to intermediate states, until you finally get to your desired goal state, and your solution to this problem is defined as the navigation from that initial state to the goal state. So this is a way of understanding what is it that we're doing when you solve a problem. So that was the 3-disc version of the Tower of Hanoi. Tower of Hanoi's problems can go anywhere up to as many discs as you want. So there is a 7-disc version is oftentimes a very popular, challenging one. And if you were to map out the problem space for the 7-disc version, it would basically look like this. So this is a representation of the 7-disc version problem space for the Tower of Hanoi. And if you zoom in on those, each of those little triangles is a different intermediate state. So the corners of each little triangle is the different intermediate states. So the top triangle there, the tippy top triangle, its top corner, or its top vertex, that is your initial state. And then one of those bottom corners on the bottom row of this diagram, one of those bottom corners, that is your goal state. And there's multiple goal states in this problem space, each of which is a successful solution to the problem. And your task, if you're doing the 7-disc Tower of Hanoi, is to navigate that entire problem space to get to the end. So without going into too much detail, you can see that this problem space gives us a sort of idea of the structure of the Tower of Hanoi. And as you can see, it's a very repetitive structure. So this larger triangle is made up of 1, 2, 3 medium-sized triangles, each of which is made up of 1, 2, 3 smaller-sized triangles, each of which is made up of 1, 2, 3 even smaller-sized triangles. So one of the ways of understanding the Tower of Hanoi is that you're basically solving smaller and smaller versions of the Tower of Hanoi every single time. So the 7-disc solution contains the 6-disc solution. The 6-disc solution contains the 5-disc solution, all the way down to the 2-disc solution containing the 1-disc solution. And again, we can get insight to that process from understanding and mapping out this problem space. So let's take a look at how these problem spaces can help us understand psychological challenges when we solve problems. And to take a look at that, we're going to take a look at the Hobbits and Orcs problem. So I will read this out for you, and then we'll pause the video and see if you can come up with a solution. So the Hobbit and Orcs problem. It goes on one side of a river. There are 3 hobbits and 3 orcs. They have a boat on their side that is capable of carrying 2 creatures at a time across the river. The goal is to transport all 6 creatures across to the other side of the river. At no point on either side of the river can orcs outnumber hobbits, or the orcs would eat the outnumbered hobbits. The problem then is to find a method of transporting all 6 creatures across the river without the hobbits ever being outnumbered. So basically what we have here is we have a river, and we have a boat, and we have 3 hobbits on one side of the river, and we have 3 orcs on the other side of the river. So that is your initial state. In this problem space, that is where you start the problem. What you want to do is you want to take that boat and you want to be able to transport all 6 of those people over to the other side of the river. That is your goal state. So we have our initial state and we have our goal state. And basically what you're going to want to do is you're going to want to apply the operator of 2 people can be in a boat in order to get it to the other side. At least one person has to be in a boat in order to get it to the other side. So the general idea is that you will send 2 people over and then 1 person back to try to solve this problem. And you need to find out the combination of people to send over and send back. So for example, your first move might be to put 1 hobbit in the boat, put 1 orc in the boat, and send that across the river. And that might be one of your intermediate states. At that point, you have to make a decision. Who am I going to send back? So in this case, you have to remember that orcs can never outnumber hobbits on either side of the river. It's fine for them to be the same number as hobbits, but it's not fine for them to outnumber hobbits. So in this case, we cannot send the orc back to bring the boat back to the other side. We have to send that hobbit. So this would be one intermediate state in the problem space. This would be another intermediate state in the problem space. So we are trying to solve this problem by navigating through all these different intermediate states. So at this point, I would like you to pause the video. Those are your first two moves, and there are multiple different ways to solve this. So if you want, feel free, back it on up to the initial state once again, and give it a shot. Try to solve this problem. Keep track. I highly recommend write this down, because according to psychological research and according to one of our concepts and theories that we're going to go over, this is a difficult problem. This is a challenging problem, but it's challenging in one specific place. So go through it, write it all down, write all your steps down, and let's see if you get stuck, or you get it's the most difficult in the place that it should be most difficult. This is almost like a cog lab where we'll see if what we're predicting happens, for all of us. So highly recommend, pause the video right now, take a few minutes, do this, write it all out, write the moves, send a Hobbit, send an Orc, bring back an Orc, send a Hobbit, send an Orc, bring back, a Hobbit, write it all out and see if you can solve this problem. And when you're done, restart the video and I will take you through the solution. All right, so were you able to solve it? Hopefully you finally got to the solution. If you did, was there a particular place that was difficult? And try to identify which move was the one that was most difficult to come up with, and we'll see if it matches up the move that psychologists have found is the most difficult one, and we'll explain why that move was the most difficult one. But before we get to that, let's take a look at the solution. All right, so one of the solutions to this, first move that you do is you take one Hobbit and you take one Orc and you take them across the river. So that's your intermediate state. Now, we're doing this because you can't take two Hobbits across. That's not allowed. You could take two Orcs across to begin with. That would be fine. But we're going to start off with one Hobbit and one Orc. At this point, on the other side of the river, you have one Hobbit, one Orc. If you send an Orc back, then on the original side, there'll be three Orcs and two Hobbits. The Hobbits will get eaten, game over. So we can only send back one Hobbit. So we send back a Hobbit. And then when we send back that Hobbit, we have to send people over the river one more time. So in this case, we're going to send two Orcs, there we go, over to the other side of the river. And then at this point, we're going to send one Orc back so that the boat can come back. And then we're going to send two Hobbits across the river. And then this is probably where you got stuck. So if you got stuck, you probably got stuck on this next move. Because if we send back a Hobbit, then the Hobbit that we don't send back is going to be outnumbered. There's going to be two Orcs and one Hobbit on the opposite side of the river. If we send back an Orc, then the Hobbit that is stuck on the original side is going to be eaten because there's going to be two Orcs and one Hobbit. So what do? We can't send back a Hobbit. We can't send back an Orc. What are we going to do? How are we going to solve this problem? This is where it gets difficult, because in this move, we have to send back two people. We got to send back one Orc and one Hobbit. So we've sent, in the previous move, let me just back it up. In the previous move, we sent two people across. And now for the first time, we got to send two people back. And then once we send two people back, we can send two Hobbits across, and then send one Orc back, send two Orcs across, and then send one Orc back, and then finally complete the problem and come to the goal state when we send two Orcs across. So these moves here and these operators, these legal moves, the operators, can help us understand the problem space for this. And again, this will be a simplified one. There's more than one way to solve this problem, and you might have solved it in a different way. But for the solution that we came up with, for your initial state, you can either make that move right there, where you send two Orcs across, or you can do this move right here, where you send an Orc and a Hobbit across, or completely legal, you can send one Orc across, right? Now that makes no sense whatsoever, because you're just going to have to send that Orc back, and you go right back to your initial state. But notice that they're all legal moves. They don't break the rules of the game. They don't break the rules of the problem. So those are all operators, ways that you can navigate through this problem from one state to the next. So let's stay with that middle state there where we took a Hobbit and an Orc across. Once you make that move, the only thing you can do, the only legal operator that you can apply, the only legal move that you have is to send one Hobbit back. That's all you're allowed to do. Everything else would break the rules. So everything else is not included in this problem space. The problem space only includes the states that you can get to by following the rules. All right, so let's zoom out a little bit. Once we get to that point there's a number of different options that we can do. But in this case, we were going to send 2 Orcs across. And then let's zoom out a little bit more. And you can see how complicated sometimes these problem spaces can get. Once we have 2 Orcs across, we can send 1 Orc back. That's really the only thing we can do is just send 1 Orc back. And then once we send 1 Orc back, we can apply another operator where we send 2 Hobbits across. Again, that's the only move that you can do because you have 2 Orcs on the other side. You can only send 2 Hobbits across. And then here is the difficult move where we have to apply the operator where we send 2 Hobbits back. That's the only legal move that we can do. And then from then we send 2 Hobbits across, and we send 1 Orc back, and then we send 2 Orcs across, and then we send 1 Orc back, and then we send 2 Orcs across, and we've made it to our goal state. So we can see how we've navigated this entire problem space, but also very interestingly, we can see that almost at every single juncture of this, there was really no choice between possible moves that we can make, right? There was never a choice, like in the Tower of Hanoi, between 2 moves. There was very rarely a choice. I shouldn't say never. There was very rarely a choice between 2 different moves. A lot of times you heard me say, well, that's the only move that you can do. We could only take 1 Hobbit back. We can only take, 1 Orc back. So considering that most of this problem space only allows for 1 operator to be applied, only allows for 1 move, what makes it so difficult is identifying what that operator is. What makes it so difficult is figuring out what the legal move actually is. What is that one thing that you can do? So this is where we get into the idea of operator selection. So when we have to choose these operators, and when we have to determine which operators we can use, how do we do that? Well, there are a number of different techniques that psychologists have identified that we use when we're trying to solve problems, when we're trying to choose which operator should we use and which operator should we avoid using. And avoidance is a good way to introduce this next one because it's literally called backup avoidance. And backup avoidance is our general tendency. It's our general heuristic. So these are all kind of heuristics or strategies or best guesses, things that typically work. These are all strategies that we use to try to navigate these problem spaces. So backup avoidance is the first one. And this is where we tend not to select an operator that undoes the effect of previous operators. We tend not to choose a move that undoes progress that we've made, that undoes the moves that we've made before. So for example, in the Tower of Hanoi, we start with that initial state, and we have this particular problem space here that we're trying to navigate. And notice that as we go through this problem space, we might end up at that particular intermediate state there. So make sure you're following the green arrows. We start from the initial state, we go down to that problem space. We then apply this operator to go down to that intermediate state. And at this point, we have a choice between 2 options. And backup avoidance would indicate that we would not choose this operator because we're going to avoid backing up to the initial state. We're going to avoid doing anything that completely undoes the effect of previous operators. This is also why people typically don't take the green disk and move it from position 1 to position 2, and then follow that up with a move from position 2 to position 1. You don't just go back and forth. And again, the reason for that, even though it's completely legal, The reason for that is this idea of backup avoidance. So we don't want to select an operator that undoes the effect of previous operators. And if our solution to the problem requires that we back up, then that's going to be a difficult problem to solve. All right, next one here that we try to do. We try to do difference reduction. And difference reduction is where we select the non-repeating operator, so not something that we do just over and over and over and over again, but we choose the operator that most reduces the difference between your current state and the goal. So if you have a choice between two operators, one of which gets you halfway to a solution, and one of which only gets you a quarter of the way to the solution, our natural tendency is to choose the one that gets us halfway to the solution, even if that leads to a dead end. And that's what might make a problem difficult, is if it takes advantage of difference reduction, our natural tendency to do difference reduction, to lead us down the wrong path in our problem space. So this difference reduction is also known as hill climbing, and it's called hill climbing because of the metaphor of a person who is, so think of this situation. If you were blindfolded in a field and there were hills in that field and you didn't know anything about the field, so you're blindfolded in this field, and I gave you the challenge of finding the highest point in that field, what you would do is you would basically walk around with the blindfold on in different directions until you felt yourself step up. And then you would step up some more, and then you would step up some more, and eventually you would get to the top and you would start to step down. And what you would do is you would kind of stay there at that top level because you have reduced the difference between being at the bottom and being at the top enough in this kind of, in this metaphorical example. So that's why it's called hill climbing. When we're solving a problem, we try to step up to the solution. We try to step up to the goal state, and we have a natural tendency to take the biggest steps possible. And that is that idea of difference reduction. So let's take a look at those. Let's take a look at the idea of difference reduction, and we're going to apply it to the Hobbit and the Orc problem to see why it's particularly difficult. And again, specifically to see why people tend to have difficulty in the same space. So again, identify that move. That was the most difficult move. We're about to see why it was the most difficult move when we take a look at difference reduction. So we're going to graph this out so that you can actually see the hill that we're climbing. So we're going to start off on the y-axis here, and that's the amount of your goal that you have attained. So you can see that there are 6 notches for that goal, and the amount of the goal is scored in terms of how many people do you have on the other side of the river. So it can go anywhere from 0 to 6. So the bottom part of that axis is 0. That's where we start the problem. Nobody's on the other side of the river. The top part of the axis is 6. That's where we end the problem. Everybody's on the other side of the river. And then down on the x-axis there, we have the number of moves that we did. So this is just a tracking of where we are in the problem in terms of how many moves did we do. All right, so we're going to start off with move 0. That's right there. And we start off with 0 people on the other side of the river. So that's where we begin the problem. That point tells us where we begin the problem. First move we do is we take 2 people across the river. We put a Hobbit and an Orc into the boat. We take them across the river. That one move takes us from having 0 of the goal solved to having 2 out of 6 of the goal solved, right? So we went from having nobody on the other side of the river to now 2 people on the other side of the river. So we have gotten closer to our final goal. We now have 2 out of 6. We are 1/3 of the way there. All right, so that becomes our new state, our new intermediate state. Now from here, we make a second move. But this move, notice, it undoes some of our progress because we got to take that Hobbit and we got to send him back over the river. So what this does is it takes us from having 2 out of 6 people on the other side to only 1 out of 6. So this has taken us further away from the goal. So in terms of hill climbing, we're going to resist this move, but just a little bit. So in terms of hill climbing, we went up to We've gone down 1. That becomes our new intermediate state. But now look what we can do. We can take 2 orcs across. So now we end up with a new intermediate state where we have 3 out of 6 people on the other side of the river. So in terms of our goal, we're halfway there. We're halfway across. We're halfway to solving our goal. We got 3 out of 6. So what do we do now? Now we have this new intermediate state. Well, we got to send an orc back. But notice that this undoes a little bit of our progress once again. We now go back to 2 out of 6. So we continue to do this. This becomes our new intermediate state. Once again, we send 2 people over to the other side of the river. We send 2 hobbits this time. Now we're really getting close. Now we're at 4 out of 6 on the other side. And that becomes our new intermediate state. And this is where this problem gets difficult. And it gets difficult for 2 reasons. Number 1, this is where we now have to send 2 people back. We have to send a hobbit and an orc back. So we undo basically everything that we did in that last move. So we are undoing that entire move. So backup avoidance is coming in, and we're undoing the progress that we just did. Difference reduction is inhibiting our progress because we don't want to reduce. We want to reduce the difference by the least amount. Right? We're really struggling to only send 1 person back. We don't want to send 2 people back. We don't want to go that far back down in our progress. And then finally, if you can think back to the previous lecture, if you can recall, this also plays into the idea of a mental set. Because so far, we've been highly successful with taking 2 people across, bringing 1 person back. Taking 2 people across, bringing 1 person back. So we were rewarded twice for taking 2 people across, bringing 1 person back. So on the 3rd time, our minds have fallen into that mental set. And we basically say, hey, you know what? Let's do it again. 2 people over, 1 person back. But you can't take 1 person back. So that's where the problem gets difficult. And once you are able to decide, oh, I got to take 2 people back, then that becomes your new intermediate state. Take 2 hobbits across. That gets us back to 4 out of 6. 4 out of 6 in terms of our amount of our goal. And then from there on in, new intermediate state, you take 1 orc back across. We only have to go back down to 3 out of 6. And then we can continue to climb the hill. Take 2 people across, send 1 person back, and then finally send the final 2 people across. And we have our solution. We've come to our goal state, and everything is solved. Now, again, this is the kind of navigation of that problem space. And this allows psychologists to identify what makes this problem so difficult. Because the difficulty that people have, the place where people get stuck in this problem is in that move right there. It's when you have to take 2 people back. And it's identifying phenomenon like this that allows psychologists to understand that what's going on here is people are avoiding that backup. They have backup avoidance. They're avoiding undoing what they just did. We just took 2 people across. We intuitively want to avoid sending 2 people back. You also want to solve the problem and get to the solution in as big a step as you can. And going up 2 and coming back down 1, going up 2 and coming back down 1, that's the biggest steps that you can take. So going up 2 and coming down 2, that intuitively just doesn't make sense. So that's why you probably had a hard time coming up with this solution that you got to send 2 people back. Because again, everything that we know about problem solving and how we're built psychologically and the strategies we use to navigate this problem space is working against you, specifically for that move highlighted in red, specifically for taking 2 people back. And that's why that particular area is the difficult part of this problem. All right, so let's continue our look at operator selection. The last thing we're going to take a look at in terms of operators is known as means-ends analysis. And this is a way that we solve problems, and it's a way of basically breaking down a problem into smaller problems. So this is when, in a problem space, we create a new goal that is a new end, And that enables us to apply a new operator that is a new means. So instead of applying one operator and solving the problem in one step, what we do is we break it up into sub-steps so that we can identify and break it up enough so that we have an operator that we can apply. We have something that we can do that we can then start navigating this problem space. And one of the things about this is that it can be recursive. And recursive is when a procedure calls upon itself, basically when you continue to do the same thing in rotation in order to solve a problem. And oftentimes what happens is that when you solve the smaller problem, then you can see that that small solution ended up solving your bigger problem, which ended up solving your bigger problem, which ended up solving your bigger problem. And you can have this kind of loop that you can work through all the way up, all the way up to the large solution. So let's take a look at an example of this. And this is going to be something that is probably going to be near and dear to your hearts. So you're welcome. So your goal in this, we'll do the schematic first. Your goal in a problem is always to transform your current state into the goal state. And that is true regardless of where you are. So that's that means end analysis. In the beginning, you're starting in the initial state and you want to transform yourself into the goal state. But halfway through, you're in an intermediate state. That's your current state. When you're halfway through solving the problem, that's your current state. So you still want to transform yourself into the goal state. So regardless of where you are in a problem, your goal is always the same. Get to that goal state. So we can apply the same strategy at every single part of a problem in order to try to solve it. And that's means ends analysis. So what we do, we'll put up a flow chart here. What we do is we match our current state to the goal state. We compare the two and we find the most important difference. And if a difference is detected, then we have a sub-goal. Eliminate that difference. That is, solve the problem. If we fail at that sub-goal, then we fail. If we're successful at eliminating the difference, then we're going to be in a new current state. And that current state is now going to be compared to the goal state. And if there's no differences, then we have success, right? We have successfully solved the problem. However, if there is, so if there's no differences, we've successfully solved the problem and we're done. So now we have a sub-goal, right? Now we've identified the new goal. The initial goal was to get your current state to the goal state. If you detected a difference, that set up a sub-goal. If you can't solve that sub-goal, then you fail. However, if you can solve that sub-goal, then you have success and you double check whether your current state matches your goal state. And if there's no difference, you've solved the problem. So now you have a sub-goal to eliminate that difference. And what do you do with that sub-goal? Well, you do basically the same thing. You search for an operator to reduce the relevant difference. You search for an operator that can reduce this difference. Basically, you try to match your current state to the goal state to reduce a difference. If you find that operator, then you match the condition of your current state to the goal state. If there's no difference, you apply that operator. If there's a difference detected, then you have a new sub-goal. And that new sub-goal, if you're successful, will successfully solve your solution. If you're unsuccessful, you're going to fail, and that's when you have no solution whatsoever. That seems a little bit more complicated than I was hoping for. So the key thing here, though, is to notice that the same thing is applied, and what you continue to do is you continue to come up with sub-goals, and another sub-goal, and then another sub-goal, and then another sub-goal, until you reach a sub-goal where you can apply an operator. And then that solves your previous problems, and then the solving of that problem solves previous problems, and then you work back up from these sub-goals. So eliminating the difference of your initial sub-goal could lead you to another sub-goal. And then eliminating the difference of that sub-goal could lead you to another sub-goal. And then eliminating the difference of that sub-goal could lead you to another sub-goal. And then eliminating the difference of that sub-goal could finally lead you to eliminating the difference of that sub-goal. And then once you have that, you go back up the entire hierarchy there, and you're able to apply operators to solve each and every higher goal. All right, so that's the idea behind means end analysis. It's a little bit complicated when you kind of take a look at it in schematic form here. So let's apply to an example. Again, something that's probably going to be near and dear to many of your hearts, if not now, in the coming years. And that is, if you have the goal of transforming yourself from an undergrad student into a graduate student, right? So you want to go to grad school. So your current state is that you are an undergraduate student. Your goal state is to become a graduate student. So what do you do, right? What are you going to do in order to solve this problem? Well, you're going to match your current state to the goal state, and you're going to find the most important difference, right? So your current state is you're an undergrad student. Your goal state is you're a grad student. So what's the most important difference? Well, you might detect that the most important difference is that you need to apply to grad school. So have you applied to grad school? If not, there's a difference detected, right? And your sub-goal now is to eliminate that difference. So you ask yourself, well, I need to apply to grad school. There's a difference detected. I haven't applied to grad school, so I need to eliminate that difference. How do I eliminate that difference? Well, this sets up your new sub-goal, complete a grad school application. So let's zoom in on that one. So we're going to complete a grad school application. And if you try to apply an operator to that and you just can't find any operators, then you're done. You failed. If you say, I need to complete a grad school application and I have no idea even how to begin, well, then you don't have any operators that you can apply to this situation. But you can find an operator if you identify the difference. So you're going to match your condition that you're in, need to complete a grad school application, and find the most important difference. So you need to, you haven't completed a grad school application, you need to complete a grad school application. The most important difference there is that you have no grad school applications. You need to find a grad school application. That becomes your new sub-goal. So now we go deeper into this and we have no grad school applications. And you ask yourself, can I apply an operator to that? Can I find that grad school application? And you might say, all right, well, what I can do is I can Google it, right? My current state is I have no grad school applications. The most important difference for that would be to find some with Google. So I'm going to Google it. So that becomes your new sub-goal. Google these grad school applications. And then if we go one step deeper, you're going to Google it. How do you do it? Well, if you're not currently in front of a computer or a smartphone, you can find an operator that says, use your smartphone, and then that will eliminate the difference, and you can then find your grad school applications. So you're going to use your smartphone. Your smartphone gets you to Google. Once you've gotten to Google, your Google gets you to grad school applications. Once you've gotten grad school applications, those get you to complete grad school applications. Once you completed grad school applications, those get you to applying to grad school. So you can see in this analysis here, in this means end analysis, you kept breaking down the goal, identifying the biggest difference until you came to a sub-goal that you could solve. Use your smartphone. That you can solve. And then again, that led you back up the entire chain, because once you got your smartphone, you could have Googled it. Once you can Google it, you can find grad school applications. Once you find grad school applications, you can complete those. And once you complete them, you can apply to grad school. Now notice that sometimes your solution of a sub-goal might require a whole new means end analysis. Because you might come to the grad school application, and you might say, all right, I got grad school applications. And then it says, all right, step number one, give me your personal statement. Now you identify the new most important difference. I don't have a personal statement. So how do you eliminate that difference? Well, you might say, I need to write a personal statement. So you identify a new most important difference. Don't know how to write a personal statement. Identify a new most important difference. Find somebody who knows how to write a personal statement. Identify a new most important difference. Book an appointment with your advisor. And then once again, once you can do something where you can actually do that, everything else can cascade up and you solve your problem through means ends analysis. So this means ends analysis, we took a look at a real life example here. It's also one of the ways to think about how the Tower of Hanoi is actually solved, because in the Tower of Hanoi, let me just see if I can bring that up here. There we go. In the Tower of Hanoi, you can break down the Tower of Hanoi down to a single disk. And then that is your base sub-goal. And then you can recursively use that same solution and go all the way back up the chain in order to solve the Tower of Hanoi problem. So if I gave you a one disk Tower of Hanoi, if I said, you know what, solve this, you need to go from that location to another location, and you can only move one disk at a time, and you can't put a smaller disk on top. Sorry, you can't put a bigger disk on top of a smaller disk. You would take a look at that and say, all right, yeah, no problem. Boom, problem solved. All right, so that's the solution of the one disk problem. The solution of the one disk problem is a sub-goal of the solution to the two disk problem. So in the two disk problem, that becomes a one disk problem stacked on top of another one disk problem. And once you solve the green disk problem, you can then solve the red disk problem and move the red disk to the new location. And then you can put the green disk on top of the red disk. So that is the two disk solution, right? So we have the one disk solution, which allows us to do the two disk solution. Well, the two disk solution then becomes a sub-goal for the three disk solution. And you can see that each of these solutions can be solved individually. So now we know that the three disk solution needs to be moved there, in which case we then have a two disk problem with the green and the red disk, which boils down to a one disk problem, which is the green disk. And you can see again that this means end analysis allows us to solve these little sub problems that we can solve and then build our way back up to solving the huge problem. All right, so we're going to wrap up today with a look at insight problems. So now that we have the idea of the initial states and the goal states, the problem space and the operators that we're moving through, we're ready to take a look at why these insight problems are so difficult, even though they require only one step. So it's easy to understand why the Tower of Hanoi problem might be difficult, because it might take 32, 64, 128 steps. It can take a lot of steps, depending upon how many disks you have. But why is something like an insight problem, like the haystack problem, why is that difficult? It's one step. It's a parachute. Boom, you're done. Why is it so difficult to find that? And in the funeral problem, why did she kill her sister? Boom, she wanted the guy to come back, right? He was at one family funeral, he'll come to another one. So these problems only require one step. This doesn't require a chain of thought in order to solve this problem. It just requires that one realization. So the question is, why are these problems difficult? And the answer comes from the problem space, the way that these problems are represented. So in the Tower of Hanoi problem space, that's the typical problem space. And as you can see, it's a multi-step solution, and you can feel yourself getting closer, right? You know when you're doing the Tower of Hanoi that you're further along than when you started, right? You know that you're kind of making progress, that you're moving disks, into new locations, and you can navigate that until you get to the goal state. And at each point in the Tower of Hanoi, there's only two operators that you can apply. There's only ever two moves that you can make at each stage of the Tower of Hanoi, if you don't count the move where you just undo what you just did. So there's only ever two moves that you can do. So it's continually easy to at least navigate or at least walk through the problem space, because you can only ever do two things. So you just have to choose between this or this. Easy to make progress in the Tower of Hanoi. It's not an insight problem because it's easy to move through the problem space. When you take a look at an insight problem, you have a start state, right? The cloth ripped. Why is it important? You have a goal state. Oh, it's a parachute. So why is that operator so difficult to follow? Well, it's not that it's a difficult operator to follow. It's because of the nature of the problem space. Because in an insight problem, it has a problem space that has many operators. So it's got a ton of these different operators to choose from. And the challenge in an insight problem is finding the right operator. So the haystack was important because the cloth ripped. That line on the left, maybe because they needed money. They were going to sell the cloth for money. Now they're going to sell the haystack for money. That's the operator on the far left. Second operator from the left, they were carrying hay in the cloth to take it to the market. Now the cloth ripped, the hay jumped out all over the place. They need more hay. They need to go back to the haystack. It became important. Third operator from the left, there's a needle in the haystack. They can use it to sew up the cloth. Fourth operator from the left, the hay. I don't know. There's a ton of different possibilities, and the difficulty in solving this problem is not in applying the operator once you find it. It's finding the operator, and we can get that. We can see that from the goal state. So the same thing with the funeral problem. There are a million reasons why she might have murdered her sister. Maybe she found out that her dream guy was her sister's secret fiance. Maybe she found out that her sister had some huge blackmail scheme that was going on. Maybe there's a ton of different possible reasons. So finding that one answer isn't too difficult once we find it. But actually identifying the operators is very difficult. And this is also why you never know if you're getting closer to solving an insight problem. You never feel like you're getting closer, because each of those operators, when they fail, take you back to the start state. So you don't know if the very next operator you try is going to be the one that takes you to the goal state, or if you're going to have to try another 100 operators in order to get to the goal state, because every time you fail, you go back to the start state. So of course you're not going to feel like you're getting anywhere, because you don't know how many possible operators there are. Maybe there's only 10, maybe there's 100, maybe there's 1,000. It's very difficult to know, hence the sort of aha moment when you finally come up with that solution. All right, so that gets us to our goal state for this lecture, slide number 106. So that's it for today's class. So thank you so much for joining me on this week 14, class number 1, chapter 12, look at problem solving and creativity. So keep yourself safe and go out there, solve your problems, try some of these techniques. Use the breaking of backup avoidance, breaking of difference reduction, and means end analysis to help you solve your own problems. And take care of yourself, and I will see you all next time.